Ladies and gentlemen, it's back in the saddle for us in our continuing study of energy. This unit is really a continuation of the previous unit. We're going to look at one of the most far-reaching laws in all of science, the law of conservation of energy. Today we're going to focus on just a subset of conservation of energy, which is mechanical energy. Let's get started. Before we tackle the law of conservation of mechanical energy and how to use it in problem solving, let's draw a bit of a map for how we got here, based on what we've studied so far. So on the screen you see kinematics equation, Newton's second law, and then the basic definition for work. I want to mathematically combine these. Let's do the following. We're going to rearrange this kinematics equation to solve for acceleration. And that looks like this, right? Just mathematically rearranging. And then what we're going to do is we're going to take Newton's second law, the F, right? We're gonna substitute that in right there, okay? But before we do that, we're going to substitute this expression for acceleration right there, okay? What we end up getting is an expression for work that looks like this, the M of ma, right? And now comes the acceleration part, and then the rest of the work formula, okay? All of that can be reduced to the following, which should look familiar to you, right? The 1/2 mv squared we defined last unit as the kinetic energy, and this expression here, okay, we defined as the work kinetic energy theorem. So you see that Newton's laws, right, is tied to the idea of work and energy. Okay, so as we work on this, what seems like a completely separate unit, work and energy, remember that there's actually a mathematical and theoretical tie-in to Newton's laws. And what that means for us practically is that instead of solving Newton's laws problem the Newton's laws way, we can solve it in the energy way. What we want to do is add one more thing to this, which is the definition of potential energy. We previously defined the definition of potential energy in the following way. Let me write it over here. Okay. The work done by a force is going to be related to the decrease in potential energy, right? One being the negative. So we can use this definition of potential energy and this definition of kinetic energy to come up with a new expression. First of all, a few definitions. Remember that conservative force is defined in the following way. We define a force as conservative if the total work it does on a particle is zero when the particle moves around any closed path returning to its initial position. When an object is lifted up, gravity does negative work. When an object falls back down, gravity does positive work, and the total work done by gravity is zero. Another consequence of a conservative force is that it's path independent. Remember we had that demo of the different slide shapes, and that the path taken by the marble from the top of the hill to the bottom didn't matter. It had the same amount of kinetic energy at the bottom. So when we talk about conservation of mechanical energy, we talk about the conservative forces, right? Every conservative force will have a potential energy function associated with it. The next definition is mechanical energy, and mechanical energy is simply the sum of kinetic and potential energy. Okay, and you can see that on the screen I've already come up with a result, the definition of the conservation of mechanical energy. Okay, we're going to take these two expressions that we derived on the previous page, right? We can set them equal to each other, and we can come up with this expression that you see on the screen. Okay, right here. That's the conservation of mechanical energy. Now, I can write that in a couple of different ways. Okay, probably the most preferred way for me to write it is simply to write it like this. Okay. And this is true whether you're speaking of mechanical or non-mechanical energy. It's just a mathematical way of writing the conservation of energy, right? But remember that the delta KE here is KE final minus KE initial, right? And then potential energy is PE final minus PE initial. So you can actually rearrange these in the following way. You can write KE initial plus PE initial. It's just different ways of writing the same thing, whatever makes most sense to you. Okay? But you want to get used to all these different expressions and realize that they're the same things. All right, let's take a look at why this can be so nifty for us. Okay, here's an example of a Newton's laws problem, right? A block on a ramp. Okay, you've already solved all kinds of problems, all kinds of variations of this problem. That would be this one here on the left, right? But what about this one here? Have you ever done one like that, where the surface is curved, right? Well, if you had to solve that problem using Newton's laws, you would have to resort to vector calculus, which we have not covered. That's not one of the tools in our toolbox. However, if you look at this from an energy perspective, right? Let's say you want to ask, like, how fast is the object moving at the bottom? Okay. Well, from an energy perspective, right? You already know that the conservative force there's a force that's acting here if we ignore friction, right? The conservative force acting is gravity, and it's path independent. Right, so all we care about with energy is that it's initial condition and its initial position and its final position, or its initial state and its final state. We don't care about what happens in between, and that's very convenient. Right, if you don't need to know about time or direction, then a conservation of energy is a way to go. And if you use conservation of energy, you can solve this problem right now. Right, if you didn't have conservation of energy, you'd have to resort to vector calculus. So what you're going to find is that the energy approach is going to make the solving of certain problems a lot easier. I want to show you on the next screen another example of a problem that we already know how to do and how the energy conservation approach makes that type of problem solving easier as well. That problem type is a projectile motion problem. So here you see an example of a projectile motion problem, right? An object's launched from a cliff or a building at a certain angle, and we want to know how fast it's going at the bottom. Okay, now remember, when it hits the ground, it's moving at an angle, so it has both x and y velocity. You could solve this problem now using your kinematics equations, but you would have to work in one dimension at a time, right? And then when you got the velocity in each dimension, you'd have to Pythag those velocities to get the total velocity. It's doable. You've done it. You're comfortable with it. But there's an easier way to do this. Okay? Remember that energy is a scalar. And so that's going to allow us to skip the whole direction thing. Okay? Let's look at this problem from an energy perspective. Let's analyze what's happening at the beginning, right? What's the initial state of the object, and what's the final state of the object, and see if we can't get our answer from there. So I'm going to write that just like this, right? The energy at the beginning is equal to the energy at the end. What you need to do here is all you have to do is figure out what kind of energies does the object have at the beginning, and what kind of energies does the object have at the end. So notice that I've defined my height as 0, right? Before I make any GPE assessments, I need to be clear about where my 0 GPE level is. So it makes sense to put it on the ground. And so if I look at my object, right, the rock or the ball, it's going to have GPE at the beginning, right, because it's being launched from a height, and it's being launched with some initial velocity, so it also has kinetic energy. Okay, but at the end, since it can't fall any lower, all it has is kinetic energy. That's all you do. You assess the energies at the beginning, you assess the energies at the end, and the rest is math. Right now, you just substitute in your expressions that you have for each of the energies. Okay. In some cases, you'll get some nifty little cancelings out. Right. We know from our earlier kinematic studies that elephants, feathers, pennies, and cars all fall at the same rate, right, in the absence of air resistance, and that's why you see mass canceling out here. If I multiply everything by 2, I get this expression that I can then solve for the final velocity, right? One equation, one step essentially, right? Compare that to the projectile motion method where you probably had to do at least 3 steps, right? You had to find the vertical velocity, the horizontal velocity, and then Pythag them. So a really nifty way to do projectile motion problems if, right, caveat, it does come at a price, if you're not concerned about time and if you're not concerned about direction. Right? If you were asked about either of those, you'd have to resort to kinematics approaches to this type of problem. Let's take a look at another type of problem that you would see, and that is problems involving springs. So here you see an object on a ramp. It's on a curved ramp. But as previously stated, that's not going to concern us too much. It's being released from rest at a certain height, h. I'm not going to use numbers in the problem, just show you the setup. And then it's going to slide down the ramp, slide across the frictionless floor, and it's going to hit that spring. And then obviously it's going to compress that spring. So what we want to know in this particular problem is how much is the spring compressed when the block comes to rest? Or what's the maximum compression of the spring? Because what will happen is the block will compress the spring, come to rest momentarily, and then shoot back to the left. So let's think about, first of all, what's my initial position going to be? What's my final position going to be? All right, so I want to define those first. Right, initial position at the top. The final position is going to be whatever that point of maximum compression is. And then what I want to do is I want to determine what are the energies of the object at the beginning, set those equal to the energies of the object at the end. Well, at the beginning, since it's not moving, all we have is GPE. Okay. Now I want you to notice something here. Obviously, as the block falls, it's going to gain kinetic energy and lose potential energy. Right at the bottom of the ramp, right here, it's going to be all kinetic energy. But notice what happens. That's not our final point, right? This here is not our final point. So what's going to happen is all that kinetic energy is going to be converted to potential energy of the spring. So that even though for a large part of its motion, the object has kinetic energy, it doesn't actually show up in this equation because all we care about is the initial point and the final point. So there's this whole transformation from GPE to KE that we don't even care about. It doesn't even show up. Right? All we care about is the initial point and the final point. This is emphasizing, again, the elegance of the energy approach, the simplicity of the approach. All we care about the initial and the final state. And then again, once you've done that, right, the physics brain work ends right here. Once you've done this, the rest is math. Right? If you've set your problem up correctly, if you have defined your zero GPE level, and also in this case, I should point out your zero EPE level, right? So this right here would be the equilibrium position of the spring. So you remember you have to measure that as well. So you want to be clear about where the zero levels are for your energies. But once you've done that, right, all the brain work, the physics brain work anyway, is done, and the rest is math. So all I'm doing here is I'm just substituting in what I have, right, the equations for those energies. Notice in this case that the mass does not cancel out. Right? Heavier blocks will compress the spring more. And then you just solve this equation for x. Right? So that's the second type of problem you would encounter. Okay, the last type of problem, springs or pendulums. You're going to find that the setup for these is very similar. It's just there's a little trick, a little geometry trick you'll need to use to find the change in height. Let's say we want to know how fast is this pendulum going at the bottom of the swing, or at the bottom of its path, right? Or in the case of a swing, how fast am I going at the bottom? Remember, you, the physicist, gets to decide where your zero GPE level is, okay? And it typically makes sense to do that wherever the lowest part of the object's motion is. Okay, so even though the ground is lower here, we don't even know how much below the bottom of the pendulum the ground is. It's irrelevant, right? It doesn't matter. You make the zero height level wherever makes the most sense to you. So, and again, we start with what's the energy at the beginning, okay, and what's the energy at the end. All right, so the final position's down here. And I think you'll see that it looks like this, right? At the beginning, assuming it's released from rest, all we have is GPE. At the end, all we have is KE. And that's going to look like this. That's not very difficult, okay? The tricky part is, how do I find the change in height? Okay, well, the change in height is right here. And to find the change in height, you just need to, it's a common geometry trick that we do this type of problem, but you have to set up a right triangle, okay? And when you do that, you'll find that this part here, right, is L cosine 40, L being the length of the string or the length of the swing. This height, however, right, is still L. It's still the full length. So that the height ends up being just the difference between those two, L minus L cosine 40. That's the height. And that's the trick to these types of problems. So, you've seen me apply energy conservation to three types of problems. Again, we're talking about mechanical energy here. And we'll expand our study to other types of energy next lesson.